Over to you, Tad.
Alrighty. Good morning, good evening, good afternoon, depending upon where you are in the world. My name is Tad Bostic, and I'm a consultant with Harvey Rock Physics. And I'll be doing some of the presenting today for this LogScope Fiber software webinar. Co-presenter today is Akas Manzoor. Akas is Director of Business Development for HRP, as we call it. And also on the line is Nick Harvey, who's the CEO. And Nick will be monitoring questions and answering those as we go along, and we'll also take questions at the end. So I'm going to go ahead and begin with a set of slides and give you kind of a high-level overview of LogScope Fiber, and then we'll move into a demonstration of the software itself. So why LogScope Fiber? So what we're looking at in the industry is a broad adaptation or adoption of distributed fiber optic sensing. This has been going on for several decades now, but it's really been ramping up over the last several years, the last 10 years or so, and particularly in the last 5 years. And it's becoming really a critical component of particularly upstream oil and gas and understanding well performance and well intervention. And that could be with permanently installed fibers or fibers that are deployed through various types of interventions. What this has resulted in and continues to kind of increase is the collection of massive amounts of data, particularly when you're looking at the distributed acoustic sensing. So hundreds of gigabytes and terabytes and into petabytes of data that need to be evaluated and make decisions that are capturing valuable information from wellbores, for example. And some of that's used, but a lot of it is just put on servers or hard disk somewhere and archive. And so there's just a lot of data that just goes unused. And it's very difficult to go back and grab this software kind of independently as a customer or a user to be able to work with that data and then to integrate that data potentially with other types of software packages or other well information. So really there was a challenge that was presented to Harvey Rock Physics several years ago by a major operator who had this particular problem. Can you put together something that can read various types of formats quickly, visualize it, and allow us to quality control it, or actually look at it and investigate it to a certain level and make decisions? So the solution from the standpoint of Harvey Rock Physics was LogScope Fiber. So they have a product, their standard product, which is a log analysis software and a WITSML reader it's called LogScope, but this was developed separately as an independent software to try to address this issue. In particular, it works and handles distributed fiber optic sensing data. And generally speaking, that's going to be distributed acoustic, DAS, or distributed temperature, although the software can actually handle other types of distributed sensing data. And it can be customized and further developed to handle other kinds of distributed sensing. But for the most part, that's what we're working with and what we'll demonstrate today. So another issue is that the distributed fiber optic sensing data can come in various formats. It can come in native formats from data acquisition systems. It can come in sort of standard formats like HDF5. It can come in seismic data formats. And so there's just a lot of different formats that need to be worked with. And then when you want to continue to work with the data, whether that's in one of those original formats or converted to other formats, one of the real goals is to try to make the data manageable, make the data size something that's not hundreds of gigabytes or terabytes even. We'll also show and discuss that the LogScope Fiber and LogScope are compatible and a means to further evaluate the data. So the requirements were, and what LogScope has become is a tool that's independent that you can just drag and drop large data files, hundreds of gigabytes. We'll show some examples of that. We'll show how you can rapidly visualize and focus on areas of interest, looking at features and features and things that are going on within the data that are critical or that you need to take some action on. It does run as independent, like I said, and it runs on Microsoft Windows. The demonstration today is going to focus on the capabilities and functionality. So it is going to walk through the various steps of importing the data or dragging the data, visualizing that. We can, reduce the data, map the data to correct for, various well or distance offsets and things like that. Spectral analysis, image processing, and data filtering are also functions of LogScope Fiber. And then ultimately you can reduce the data and export it to various formats. In particular, the DLIS format is a format that can actually be integrated directly into LogScope. So without any further ado then, I'll just get out of that and we'll start the demonstration. So the first thing we'll do is we'll just open up a instance of LogScope Fiber. And I'm going to be pulling in a data set here that's, if you can see on the bottom here, is about 2 gigabytes. So the process is just to drag and drop the data into the window. Then we'll go ahead and select the type of data. Sometimes it's raw, might be a HDF, acoustic, etc. SegY. We'll just go ahead and visualize that data. And so we kind of very rapidly have gotten 2 gigabytes into the visualization screen. We're looking at some acoustic raw. This particular data is in a format of a data acquisition system, native format. It is data complements of WellSense technology, our friends over there. It's a fiber line intervention data set. And so we've got a fiber line intervention tool that's being deployed in a well that's moving down the well from top to bottom. And so we'll be looking for the acoustics related to that as the tool moves into the well. On the left axis is the well depth in this particular case, where we can just toggle between feet and meters. We have the time scale along the base. We've got about 2 kilometers worth of data showed here and about a little over a minute worth of data. So 2 gigabytes in a minute. So this data set was recorded at 5 kilohertz. And that's the kind of data volumes that you'll get with distributed acoustics. Nice function in LogScope Fiber is you can view what's called the metadata. So if you do have header information in the data, you can visualize, you can look at that, and you can look at some of the key parameters, the sample rate, pulse repetition frequency, and pulse width, and things like that, which are key parameters for distributed acoustics. But it can give you a kind of a history as well as we move along and apply different filters and steps to the data. It keeps a log of that as we go along. So that's a nice thing to reference, especially if you're looking at some old data. So what we've got here, like I said, we've got a fiber line intervention deployment. You can kind of see an energy package moving down the well. There's a big white line here, and in wellbore data acquisition, a lot of times you'll have a surface cable. So we've got about 200 meters of surface cable. So the wellhead would be at the white line. Like I said, you can do some mapping and you can shift that data to get that to a particular zero reference point. Like for example, for a wellhead, you can stretch the data if there's a known correction that needs to be made for the overall length of the fiber. Can handle wrapping of the fiber around pipes, for example. Can do time offsets to correct for, say, UTC time or local time, et cetera. And then that can be preserved for the rest of the sequence of the analysis. So we're really just going to look at this package of energy that's going down the well. So really the first thing you'll do is just draw a box, zoom into the data, and kind of get a little bit closer look at some of the features. Clearly, again, we can see some energy going down the well, maybe around 500 meters. There's something that may be getting either generated by the tool or just being generated in the well. So we kind of want to see if we can get a better look at those. When you first bring up the software, it's in normalized view, so it's normalizing to the maximum amplitude on each individual trace. There's a sort of a default color scale from blue to red for low amplitude to high amplitude that you can see on the bottom here. But we can actually switch out of that and go into a unnormalized view, which will actually start to define the actual amplitude values that you're working with. So the scale along the bottom now is from the lowest amplitude value to the highest amplitude value. And if we just click on that bar, then we can actually look at those values and look at the amplitude distribution. And if we want, we can make some changes. So for example, we could just zoom into a particular area of the data and just see what's going on in that particular range. And that might change the color scheme and highlight certain aspects, maybe not. We can also change the color range, color scale, and customize that and bring in all kinds of predefined things like grayscales, and we'll see some examples of that later in the presentation. So we'll just jump back here to the default, which is auto scaling of the data itself. And again, this data set is kind of showing something happening, but it's not so intuitive. One of the first things we like to do is there's a feature that's fairly quick. It's called binning, and it's basically smoothing the data set. So we can choose to apply a bin. In this particular case, we might want to just do something fairly simple like define 5 samples per bin. That's going to give us about 1,000 bins per second. It's kind of a crude kilohertz filter, but it's just going to do some smoothing. So it's summing and averaging and outputting a particular bin. And if we just select that, it'll race through this this data set here, and we'll see a fairly dramatic impact on the data already just by doing a simple operation called binning. And what you can see here is much more clearly there's evidence of a tool that's moving down into the well from left to right over time. There's some acoustics related to that. Let's say the tool bouncing off the tubing or the casing, for example. We still got this event here in this 500-meter range, and it's still not, really, it's kind of buried in sort of signal to noise, but we do kind of like this binning output. So we can just preserve that at any time. We can export that data set, and it can be reused, reloaded, refiltered, trimmed, etc. So it's very easy and simple just to export, outputs of your operation. So we'll just hang on to that one. And the nice thing about LogScope Fiber is you can open up other windows, and we can start over, or we can work on things in parallel. I'll pull that data set in. It's already been trimmed for the surface cable to get rid of that. And at this point, we may want to go ahead and look at the data in more detail. So again, we'll just zoom in on that sort of downgoing event. One of the next recommended step would be to look at the energy spectrum of the data. So there is an ability to do FFT analysis on the data. It can choose different FFT windows from 128 to 4096, for example. We can change the scaling to logX, normalize, logZ. logZ is kind of a nice one to look at. And then what you do is you literally can just step through the data in time from left to right, and just walk through the data and look at the frequency content as you're moving through. And this is just a good way to just get a feel for how the frequencies are changing throughout the data. And then in this particular data set, as you move from left to right, you can see that the energy is moving down the well, sort of the broadband energy, and above where the tool is located, you've got lower frequencies. You can set this into playback mode, which is nice because then you can record that, or you can just set back and watch the thing play out. And you can speed it up by just changing the steps of the traces instead of every single trace to like every several seconds, for example, if you want to do a quick look. But again, just looking for just general frequency content of the data to help you decide what kind of filters you might want to apply to the data. Now there is a way to do that kind of in a batch mode, and it's called energy extract, and that will allow us to do some frequency band outputs. In this case, we also can select the FFT size. We can choose the bands, for example, that we would like to see. Just put a few of those in here. And what that's going to do is it's going to output multiple individual bandpass files from 5 to 10, 10 to 50, 50 to 100, etc. So we would output that. In this case, for this 2 GB data set, it'd take a couple of 2 or 3 minutes to do that. So in lieu of actually running that in the background, I'm just going to go ahead and show you a screen dump of what the output of that is. Now, what will happen is the individual files will be created separately. So there's separate individual files that you can go in and continue to work with. So what I'll do then is go ahead and open the image file that will show the output. Zoom in on that, sorry. So you've got individual panels here. Like I said, we just opened up multiple LogScope windows. On the left-hand side is the raw data of that particular frequency bands that I chose. And then you can also see that the other outputs of the individual files are the individual bandpass filters. So 50 to, or 5 to 10, 10 to 50, 50 to 100, et cetera, all the way up to 500 to 1,000. And what this is really showing in a very rapidly, these data sets, by the way, are only about 7 megabytes out of that 2 GB data set. But you're seeing features of the tool moving in the well, you're seeing this other feature, and really within a, say 10 to 100 hertz or so, you could potentially highlight more of this particular event to go ahead and dive into to do some more analysis. So we'll go ahead and pick a filter. So we got the digital filtering operation that is also available. We have a couple of different options, kind of a rectangular window filter and a Butterworth filter. We tend to like the Butterworth filter for the way it preserves the passband frequencies. But you can actually choose low cut, high cut, and bandpass. We'll just slap a bandpass on here. 10 to 100, for example. We've got a couple of different options on the filtering here that some of this is part of our development process, and we'll probably get that to a single option, but we can decimate the data, which is key because at 5 kilohertz, and we have still a fairly large data size. So we may want to reduce the sample rate because we're only, cutting off at 100 hertz. There's an auto feature, which is very nice, which I'll go ahead and just kind of take the guessing out of it and select a nice sample rate to be able to handle the frequency band. So we can output that. We'll call it test bandpass, and we'll just go ahead and launch that, and it's going to create a separate independent file that's filtered. And again, you could bring that file back in and do some further operation to that. I'll go ahead and open another window just in sort of in preparation for that file being created. And I think what I'd like to do is we'll go ahead and look at the comparison between the binning and the bandpass filtering that's gonna go on here. I'm just about done here. There's a progress bar that helps you understand what's going on with the operation, and at the end you'll get a little pop-up window that shows you this took 43 seconds to run that particular bandpass filter. So we'll go in and we'll find that filter, test bandpass filter here. Oops. And we'll load that up. Get rid of this here, minimize that, and we'll be looking at the raw, the binned, and the bandpass filter. So focusing on the bandpass filter now for a couple of minutes, we'll go ahead and maximize that, and we'll move that into sort of our unnormalized view. We'll zoom in on the area that's a little bit faint at the moment. We'll change that in a moment. We'll go down and select some amplitude distribution. In this particular case, because it has been bandpass filtered, it's a little bit better behaved in terms of the overall distribution, so we can kind of squeeze in on that, that distribution a little bit and see if we can get a little bit more definition on this. And hopefully you can see then that, now we really have highlighted some of this energy that's scattering off of this tool descent, or at least being generated in that particular area of the well. And just to put all of those together, then, we can do these multiple displays of the input data, the binned data, and the filtered data. At this point, we'd be maybe liking what we see. We want to go ahead and export this to the DLIS format and start looking at this and correlating this with other well information and well logs. And that's what Akash will do here in just a few minutes. The last example I wanted to show was the ability to look at some DTS data. That's not super exciting, but we'll go in and look at a DTS data set. This is about 600 traces of DTS from a cement cure evaluation. When you're looking at the DTS, go ahead and maximize that. You're looking at temperature, so we'll pull up the temp, which is representative of the temperature. And what we've got is just a lot of DTS. There's about 3,800 feet of data here. There's a surface cable from the data acquisition, so we might just want to zoom in on the pertinent data, which is the well data. And we'll see some of the results of the heating that's going on in the well. And not much signal processing that you can do with DTS, but you can go in and actually select temperatures that maybe you just want to boundary this from, say, 80 to 135 degrees Fahrenheit in this particular case, and it'll sort of bring out some of the change the color schemes to be a little bit more easy to interpret. So that's about it that I'm going to show you for the DTS, and we'll just kind of leave it at this for now with the different DAS data sets and the DTS. And at this point, I'll turn it over to Akash, and he'll show you another example of a fairly large DAS application in a different application, and then how to take this kind of data and put it into LogScope. So Akash, over to you.
Thanks, Tad. So I'm going to switch over to my screen. Please let me know when you can see it.
I can see it, Akash.
Okay, great. So what we are looking now at is a more traditional acoustic fiber optic data set. In this particular case, this is a subset from a permanently deployed cable. The file size in this case is 262 gigabyte. So I'm going to drag and drop this file into the LogScope Fiber window. And then we can select, this is again raw data. So, and we can immediately, you can see what is there in that 262 gigabyte data set. In this particular case, we can see very clearly that the well was shut in at the time that this data set was acquired, and then they started flowing the well somewhere around 4 o'clock in the afternoon. I can see some features. So what I'm going to do is I'm going to quickly go in and select a subset of data, let's say from 3,300 meters to about 3,800 meters, and from about 4 o'clock in the afternoon till about 4:10. So when I do that, we can zoom in to that particular window right away, in which we were seeing some anomaly or anomalies based on the acoustic behavior. And what we see now is clearly a pattern here showing that there is some movement going on. And in this particular case, it is a channel that is describing the fluid flow. What I can do now is unnormalize the data. So look at the true amplitude variation, and I can then look at, just give me a minute here. I cannot see. I'm going to have to select a different scale for the viewing over here, because when it goes to full scale, I cannot see the color bar. So in this particular case now, we are still looking at, so I can then unnormalize the data, uh, and select a color scale. So now we can look at the distribution of the amplitudes uh, within this window, and select, say for example, from 34,000 to about 50,000. So that's the range of amplitudes that we see. So here is a look at the data in a different view, which is showing the relativity of the amplitudes from one trace to the next. We can also choose a different color scheme. In this particular case, you can add colors, you can change colors, or you can load saved color schemes. In this case, this is a sort of a modified grayscale. And when we apply that, we can see that sometimes the data shows up, the anomalies a lot better in different color schemes. So then we can export this data set. And in this particular case, we can export a range of depth. We can export a range of time to focus on this particular event. And we can also look at exporting the frequency content. So it can be both in linear and logarithmic scale, or we can also select based on the data that we saw during the uh, FFT view. We can say that, okay, we only want to look at like a 1 to 1,000 hertz. So that's basically what we can do in order to uh, look at a subset of the data that is showing some behavior that is of interest to us. So in this particular case, the path taken by the fluid as it was flowing into the well or away from the well. So we can export that to a DLIST file, and that DLIST file then we can open up in LogScope itself. In this particular case, the first track is data from another survey, which includes the gamma ray in green and then the gas flags. The second track is the total energy that we saw from the acoustic data set. The third track is the acoustic data itself. The fourth track is the DTS from that same well. In this particular case, I have displayed both the temperature as an array and as a single curve. The second last track is a frequency panel from 1 to 1,000 hertz in logarithmic scale. And then the last track is the frequencies from 1 to 100 hertz only, because I could see that there isn't much above 100 hertz in this particular data set. In addition to that, if we have any information regarding fractures, open fractures or perfs, perforation zones or other channels, we can also bring that information in so that we can study as to where the fluids are going or coming in to the well. In this case, the well is actually deviated well, and I can look at the deviation plot, and here you can see that the well starts to deviate around 2,500 meters and then is almost horizontal. when it gets to the deeper section. What we see above and below the well trajectory are the curves from the data itself. The curve above the trajectory is the total energy as a function of frequency. And we can say that there are two major zones that are contributing to the anomalies that we see in the acoustic data set. Below the trajectory of the well is the gamma ray and the gas curves. Now, these can be changed depending on what you want to see in the plot view. So coming back to the plot view, one of the good things we have about LogScope is that we can add tracks, we can move curves from one track to the other. So let's say, for example, I can add a track here, let's say a linear track, and I can import other log data. So if we have PLT data, like the spinner data, temperature data, pressure data, any other reservoir performance or reservoir monitoring data, that can be imported as well. It can also be image data from the imaging logs to be able to see where the open fractures are and how those fractures may be contributing to the flow in this particular well. I can also move curves from one track to the other to be able to correlate data with other anomalies that I see in this particular data set, or I can move it back and then also be able to delete any particular track that I may not want to see in this data set. For this particular well, unfortunately, the DTS data didn't go all the way down. So what we see over here is that the DTS actually stopped somewhere just above 3,400 meters. But we can see that the major contribution is coming from these two zones, which is from 3,500 meters to about 3,750, and then from about just around 4,000 to about 4,075 meters. So that brings us to the end of our presentation. Thank you for your attendance, and we look forward to your questions and comments. Back to you, Tad.
Okay, thanks, Akash. I'll go ahead and ask Nick to maybe comment on some of the questions that he's been reviewing. If you're there, Nick. I see some of the questions. I'm looking at them now. It's kind of hard to do while you're presenting, but the there was a question about the two of the well sense data. That was the the fiber line intervention tool that I was displaying. This webinar will be recorded and available online. I think we'll have a link to it on the website. If you if you can go to the website, which is harveyrockphysics.com. There's loads of information on LogScope, and there's increasingly more information on LogScope Fiber. I think there's info@harveyrockphysics.com is also an email contact.
Two more questions, Tad. There's a question on multilateral wells and a question on how it will be applied.
I'm sorry, what was the first question?
For multilateral wells.
Multilateral wells. Well, that's a good question. What you typically would get is, I guess, on in the case of distributed fiber optic sensing, is there'll either be a fiber running down the main bore, or there potentially could be some fiber exiting out into one of the laterals. So you'd really treat those fibers as different data sets. Like I showed before, you can pull up different windows of LogScope Fiber. You could pull in one of the fibers into one window and the other into separate window, and you could evaluate those kind of simultaneously in a couple of different instances of LogScope Fiber. Of course, once you export it, then you can bring both of those curves into LogScope and be simultaneously evaluating those, as Akash was showing.
Well, if there's no more questions, we thank you for your participation and look forward to your feedback.
There are actually two more questions. There's conversion from HDF5 to SegWi. That's in, I guess I can answer that. That's scheduled for a future release. And a question on depth shifting fiber optic data.
On the depth shifting of the fiber optic data, so there's several options there. You can just do a static shift, which will, apply the correction either positively or negatively, or you can do a linear mapping, which can help if you have an overall fiber length, which may be different than the known well length or the distance that you're actually traveling. So you can spread that across with a mapping, a linear mapping. You define the start and the end of the data set. And one thing to note on the previous question is that the software can already read SegWi indirectly. So there are some data sets out there that are being generated into SegWi, DAS data sets.
This question from Scarlett Cicino on DTS and DAS, correlating frequency response to completions optimization.
What was that question again? I'm sorry.
Question on how much work has been done correlating frequency response to the data and completions optimization, and has the software been used to optimize completions optimization?
So Nick, you can answer that one.
Well, I guess I haven't used the software myself for doing completions optimization, but I do believe that that's kind of the primary function of using the data with the fly tool by WellSense.
And it's really, this is kind of a little bit early in the game with the software as it's being, adding more functionality and features to it, whether it's a fiber line intervention or, just a temporary well intervention or permanent fiber. So, I think what we're seeing and hopefully showing today is that, it's got all the tools to be able to start to integrate these data sets together, and particularly when you get it into the LogScope domain and working with the data in the DLIS format. Those are much smaller files. These are very convenient files to be sort of generated in a field domain, field operating setting, and then uploaded quickly to servers and back-end servers for analysts to be working on the data, unless you have an actual analyst on at the well site or in the field. But the small data sets lend themselves to very quick integration and analysis of multiple types of data, and that's where you would be looking at completion data and optimizing potentially completion, looking at completion protocols, or just evaluating the completion effectiveness.
There's a question on, is there any application to Petrel models?
Well, going back to the completions optimization, Ted, the data has been used to identify leaks, so for well integrity purposes, to where patches can be set or cement can be squeezed in order to be able to bring the well back under control. So I did want to mention that. So that's kind of like part of the completion optimization.
Yeah, that's more of that's a good point, a good example of, being able to do quick analysis even in the field. And
Yeah.
I'm not able to answer the Petrel question. I have to turn that over to Nick, either you or
Yeah, basically, yes, that was the fundamental reason for designing it with DLS output, is to allow external packages to be able to pull in very quickly the data, rather than have to wait for the data to be for somebody to develop HDF5 encoding module for such software as Petrel and so on. You can just immediately output the stuff in DLS and away you go. And with LogScope, you can sort of output as LAS, DLS, LAS3, variety of other formats as well.
So Nick, can you wrap it up, please, if there's no other questions?
I think we've answered all the questions, and as Tad said, look on the website. If you register on our support website, you can get detailed information from the manual, knowledge base articles, and other stuff. Yeah, thank you for your time.
Thank you very much.